In this video, we're going to look at some of the characteristics of polynomial functions, and there's three main areas that we look at. We try to determine the end behavior and the behavior in the middle, which would tell us the number of terms it would have, or maxes or minimums, and also determine the number of roots. And the first thing that we're going to discuss is the leading term test. The leading term test is in reference to a polynomial written in standard form, which means that the highest degree term is written first. And what the leading term test tells us, so I'll highlight this. Leading term test tells us is that if I have a polynomial of n degrees, so the biggest exponent is n, and if the exponent is even, the end behavior of this function will, both left and right sides will point in the same direction. They'll either both go up or they'll both go down. And the way we would tell which one it does is based on the sign of that term. If the sign of that term is positive, both left and right sides will go up, which means that we can describe their end behavior using limits, meaning the limit as x approaches positive infinity. As I go off to the right, it will equal infinity, which means that I'm going to continue to increase without bound. As x decreases without bound, I continue to go on to the left, I still go up. Likewise, if the coefficient is negative, that means both left and right sides go down. So negative coefficient for even degree polynomial, left and right sides will go down, and then we can write the corresponding limits that describe that behavior. And the other option is if the highest degree term is odd. If it is odd, that means left and right sides will go opposite directions, much like x cubed. Now notice we're forgetting about the middle behavior here. The leading term test tells me end behavior only. And so if this polynomial has a positive coefficient for the highest degree term, it will look a lot like positive x cubed in terms of its ends. Left side will go down, right side will go up, which means that I could write this end behavior using limits. As the limit as x approaches negative infinity will equal negative infinity because it's going down. The limit as x approaches positive infinity will equal positive infinity because as you go right, it goes up. And then likewise, if the coefficient was negative, it reflects this whole graph, and left side goes up, right side goes down, and I could write my end behavior limits accordingly. So the leading term test will tell us the end behavior of our polynomials. Now we'll start talking about the fundamental theorem of algebra. And the fundamental theorem of algebra allows us to make some assumptions about what is happening in the middle of the polynomial. And the first part of it is that we'll talk about is a polynomial of degree n, so the largest exponent, will have at most n minus 1 relative extrema, and that includes your maxes and mins. So if I had a polynomial that is degree 3, this polynomial can have no more than 2 maxes or mins. If I had a polynomial of degree 4, it can have at most 3, so 1 less than that exponent's relative extrema. That's all it tells us. It tells us it doesn't tell us exactly how many there will be. It just kind of tells me, all right, well, what is the maximum number? Now, the fundamental theorem of algebra does tell us the number of complex zeros that will exist for a polynomial. If a polynomial of degree n, or if I have a polynomial of degree n, the polynomial will have n complex roots. Now, remember that a root is a zero. It's not necessarily an intercept. And the fact that we're including complex numbers means that I could be talking about real roots or imaginary roots, and so all of this part factors in. So polynomial degree n will have that many zeros. Complex roots written as a plus or minus bi, where b represents the imaginary part, a is the real part. Any number, even our whole real numbers, can be written as complex numbers because the imaginary part is 0. So that's why the fundamental theorem of algebra can be very helpful. It includes the real number roots and the complex number roots. If I have a root in a polynomial that is either imaginary or irrational, then the conjugate is also a root. And examples of conjugate pairs are as follows. If I have the imaginary number a plus bi, its conjugate root is a minus bi. Just change the sign in the middle from positive to negative. If I have an irrational root, same rule applies. A plus b times square root of c, its conjugate pair, a minus b square root of c. And so if I'm given one of the pair, then the other conjugate pair has to also be a root. And lastly, we have the factor theorem. So the factor theorem, what it tells us is that if I have a polynomial and the polynomial has zeros or roots at x is equal to a and x is equal to b, then those roots must also be factors in the form of x minus that number. So if I had a root of x equals a, x minus a is a factor. If I had a root at x equals b, x minus b is a factor. And so that helps us to look at maybe a factored form or to determine how to factor a problem in order to solve it. And so let's start applying some of these to look at some polynomial functions and start to get some analysis for their characteristics. And so what we want to do in here is we want to state the number of possible zeros, the number of relative extrema, and what the end behavior is. And all of this really looks at the degree of the polynomial. So the number of possible zeros that we could have, well, this polynomial is degree 2, which means that we will have 2 complex roots, or complex zeros, same difference. According to the fundamental theorem of algebra, we will have at most 1 relative extrema. And lastly would be the end behavior. Well, the end behavior of this, I have to account for the coefficient in front of the highest degree term. And so we're even and positive. So positive coefficient, even degree, which means that both sides are going to point up, and I could write those limits. So it would be the limit as x approaches negative infinity for this function is going to equal positive infinity, and the limit as x approaches positive infinity for this function will also equal infinity. All right, let's look at the one right here beside it. So same mission here. We want to determine the number of possible zeros, relative extreme, and the end behavior. So I'm looking at this highest degree term, and we have a degree 3 polynomial. So a degree 3 polynomial, according to the fundamental theorem of algebra, will have 3 complex roots, or zeros. Doesn't matter which one you want to write. Those words are interchangeable. It will have at most 2 relative extrema. So it could have at most 2 relative extrema. All right, possible. Can't have more than 2. I could have 0, but it's somewhere in that range. All right, and lastly would be our end behavior. So again, we're positive for that coefficient, and we're odd. What that means graphically is that we're going to have the left side go down, right side go up. And we could write our end behavior limits accordingly to be the limit as x approaches negative infinity for this function of x. The left side's going down, so we'd say equals negative infinity. The limit as x approaches positive infinity for f of x. The right side goes up, so we say equals positive infinity. And we get 2 more cases here. So looking at the third one, highest degree term is x to the 5th. So we have a degree 5 polynomial. So fundamental theorem of algebra tells us there'll be 5 complex roots. And it'll have at most 4 relative extrema. All right. Now we talk about end behavior. Well, this one is negative and odd. So negative and odd means left side's going up, right side goes down. And we can write our end behavior accordingly. So the limit as x goes way off to the left, x heads towards negative infinity. This function of x is going to be going up without bound. And the limit as x heads towards positive infinity, meaning continue to go to the right, this function of x will continue to decrease forever. And last case here, even degree polynomial with a negative coefficient. So we have degree 4. Fundamental theorem of algebra tells us there'll be 4 complex roots, or zeros. And we'll have at most 3 relative extrema. And lastly, we want to do this end behavior. So we're negative and even. So negative and even. Even means both sides point the same direction. Negative means both sides go down. And the limits for that would be the limit as x approaches negative infinity for this function of x. So as you go left, the ends of the graph are going down. As you go to the right forever, the ends of the graph also go down. Now let's start applying the factor theorem. So the factor theorem allows you to start constructing the actual equation for the polynomial if you have given zeros. Now we want to write a polynomial of least degree with integral coefficients, so we want to avoid fractions, and we're given these zeros here. So I'm given the zeros, x equals 0 and x equals 5/2. So, and I want to turn that into my factors. And so, according to our factor theorem, what that means is I could write these factors as x minus the 0 itself. So I got one factor of x minus 0, which is really just x. And my other factor here would be x minus 5/2. Now we want to avoid fraction coefficients. So even though this one is right, we want to write this one a little better. So what I'm actually going to do is I'm going to take x equals 5/2, and so I can write it with whole numbers. So I'm going to multiply by the denominator, and then I'm going to subtract the 5 over. So we'll get 2x minus 5 is equal to 0, and there's my factor. So the factors we're going to use are x and 2x minus 5. My factor, so the polynomial could be written in factored form as x times 2x minus 5, and we'll just multiply this thing together. It makes 2x squared minus 5x. Now let's go to another one. So now I have the zeros of 1, mult 2, and I. Well, multiplicity, that tells you the number of times that zero will zero out a function if you were to factor it out. And so really what we have is we have the 0 of 1 that happens twice. And so I have x equals 1 multiplicity 2, which means that factor would be x minus 1. The multiplicity 2 part means that you square that factor. So there's 2 of those identical factors. And then now we have I. Now remember, according to part of our fundamental theorem of algebra, if you have that complex root, you have to account for its conjugate. So that means I also have to account for negative I being a factor. And so we have x equals positive or negative I. Now how do we engineer the factor that created the x equals positive or negative I as my complex zeros? Well, what you would do is basically we're going to go backwards from the way we would solve a problem. The plus or the minus is created by me taking the square root of a square and having that absolute value. So what I'm going to do is I'm going to square both sides here. And if I do that, that's going to make x squared equals, remember I squared is negative 1. And so this factor here would be x squared plus 1. There's my second factor. So written in factored form, we'd have x squared plus 1 times x minus 1 squared. So I just multiply them together, and I'm going to go ahead and do that to see this thing fully expanded. Okay, here we are. We're at a new problem. We have zeros that are the square root of 2 and negative 3i. So given this, if we were just asked what the degree of the polynomial would be that would have those roots, my answer would not be 2 because we have an irrational root, which means I have to account for its conjugate. So negative square root of 2 is a 0. And I have a complex root, so its conjugate would have to be accounted for also, which would be positive 3i. And so we actually have 4 zeros here, so we're going to have a degree 4 polynomial. So let's figure out how to make the factors that have those zeros. For me personally, anytime I have a complex or irrational root and I'm dealing with the conjugates, I work with them both at the same time. So I'm going to say x equals positive or negative 3 times I. And then I'm going to work my way backwards from how I would get that answer if I was solving for x. I'm going to square both sides. It's going to give me x squared equals. Now 3i to the second power is going, remember I squared is negative 1 and you squared a 3, so I have negative 9. So I'd have x squared plus 9 is equal to 0. There's one of my factors. And then I would do the same thing for the square root of 2. So I'd have x equals positive or negative the square root of 2. And then we go through and we're going to reverse engineer. So I'm going to square both sides. And that would give me x squared is equal to 2. And then move the 2 over. We got x squared minus 2 is equal to 0. There's my second factor. So in factored form, this polynomial would be x squared minus 2 times x squared plus 9. And then we would just multiply it out. Last one. We want to write this polynomial of least degree with integral coefficients. We have a 0 of 1 minus the square root of 5 and a 0 of 2 plus I. Now, we have an irrational root, so we have to account for its conjugate to also be a root. So 1 plus 5i has to be a root. And we have a complex root, 2 plus I, so we account for its conjugate of 2 minus I. And so we're going to work and try to reverse engineer what created those factors. So we'd have x equals 2 plus or minus I. That accounts for the conjugate pair there. And we want to reverse engineer how we got that answer for x. Well, what you would do is you would isolate the plus or the minus part. So we'd have x minus 2 is equal to positive or negative I. And then we would square everything. So if I squared everything, that's going to give me x squared minus 4x plus 4 is equal to negative 1. And then set it equal to 0. So x squared minus 4x plus 5 is the factor that created the zeros 2 plus or minus I. And we're going to do the same thing for the irrational root. So x equals 1 plus or minus the square root of 5. Isolate the plus or the minus. And then we're going to square both sides. And that's going to give us x squared minus 2x plus 1 is equal to 5 and set it equal to 0. So x squared minus 2x minus 4 is equal to 0. Now, we just multiply those products together. So in factored form, that polynomial would be x squared minus 2x minus 4 times x squared minus 4x plus 5. And then if needed, we would multiply it all the way out. And I'm going to go ahead and do that. Okay, now let's take what we just did and let's apply that to helping us write the equation of a polynomial from a graph. And so one of the first things that you have to do in order to accomplish this goal is we need to be able to correctly look at a graph, identify the zeros from the graph, and their corresponding multiplicities. So we're going to start here with the graph on the far left. And so I'm going to go look for my zeros. I got a 0 at x equals -5. So I'm going to write that down. Now, the multiplicity of that 0. If I was able to zoom way in on that 0, and look, notice how the more you zoom in at on that 0, the graph passes straight through. It starts to resemble that of a line. So since it resembles that of a line and passes straight through, we're going to say that's a linear, it's going to be a linear factor, or it's going to have a multiplicity of 1, and we're not going to write the multiplicity of 1. The second 0 we see is at x equals -2. Notice how that graph, it touches the axis at -2 and then comes back from the same side it came from. Locally, inside of that, it looks kind of like a parabola in here, where it touches and goes, and it has that nice little bend through there. We're going to call that multiplicity 2. So if it looks like a parabola at that 0, we're going to say it's a multiplicity of 2. And there is one more 0 we have here, and that is at x is equal to +3, and that one passes straight through like a line. That one's actually real easy to see, straight through there, multiplicity of 1. So I got x equals 3. Now, we want to write this polynomial in factored form. So we would have y equals, now remember, all of the zeros in this list can be written as factors. So it'd be y equals, we'd have x plus 5, x minus 2, or x plus 2 squared, times x minus 3. Now, that is the equation of a polynomial that would have those zeros. Now, we have a given point. We are told that this graph has the y-intercept of 0, -12. So I need to ensure that happens. So what we do is we account for some coefficient in front of those factors, call it a, such that if I put in the point x is equal to 0 and y is equal to -12, I would be able to solve for a, and my graph will have that y-intercept. So we're going to do that, and I wrote a -2 instead of a 12. So we're going to put in 0 for all of the x's, and we're going to solve for a. So I have -12 equals a times 0 plus 5 times 0 plus 2 squared plus 0 minus 3. And then we're going to see what a is. So -12 equals a times, and we'd have 5 times 4 is 20, times -3 is -60. And then we would divide to get a. So -12 over -60 is a, and then I can reduce that. To 1/5. So I got a. So my equation here for this polynomial would be y equals 1/5 times x plus 5 times x plus 2 squared times x minus 3. All right, and we'll do this one more time. So looking here at this graph, and I have the same goal, to write the equation in factored form. We're not going to multiply this all the way out. And to do so, we start by writing our zeros and their multiplicities. So the first 0 we have is at -4. So I have x equals -4. Its multiplicity is 1 because it passes straight through. Then I have a 0 at x equals -2. It touches and comes back onto the same side it was before that 0, so that's a multiplicity of 2. I have a 0 at x is 0. Passes straight through like a line, multiplicity of 1. And then we have x is equal to 3. Now notice the behavior at x is equal to 3. How it kind of bends its way through there. It bends its way through there. Inside, or right there close to that graph, it looks like x to the third power. We're going to call that multiplicity of 3. And so now we take those zeros, and we're going to write this polynomial in factored form, like we did before. Now, we have to account for the fact that there is a point on this curve that is defined for us to use other than the x-intercepts. So we're going to have to solve for a again. So we're going to say y equals a times, and then we got to construct these factors. So it'd be x plus 4, x minus 2 squared, or x plus 2 squared, and then x minus 3 to the third. Now, what that point gives us is this point tells us that when you put in 1 for x, y must equal negative 18. This is how we solve for a. So we'll say negative 18 equals a times, and I go put in 1 for my x's. So it'll be a times 5 times 3 squared times 1 times negative 2 to the third power. And then we have to work our way to try to solve that. Now we take that, we just put that in for a, and we have the degree of our polynomial, or we have the equation of our polynomial factored form.